Okay, so the matrices, they were constructs as we are showing in the previous session. We can sub-partition a large matrix by, as shown here in this slide. And what is interesting is that in working with matrices, so let me write something like this: a matrix which can be 4 by 4, this can be equal to 1 minus 1, 5, 0, 7, minus 1, 2, 3, 9, 6. 17, 13, 21, 1, 0, 1. So for example, here we have a 4 by 4 matrix, and often what we can say is that matrices are expensive computationally. So if you want to compute something, they're expensive, and the expense is not anymore in money, but it's in time. Okay, so if you need to compute something for a week, if you have a good computer, you can do it in a day. If you have a bad computer, it will take 2 weeks. Really, sometimes the number of the size of the data set, which can be represented as matrices, it can be so huge that it might simply be expensive. And then, in this case, if you want to multiply two matrices where we have A 4 by 4 and B 4 by 4, if we want to multiply these, there is also this is just an exercise, okay, where this is a very specific example. It has been proven mathematically that if you have two large matrices, such as, but we're not talking about 4 by 4 and 5 and 4 by 4, but if the matrices are, let's say, I'm exaggerating, 400 by 400, if we want to multiply these, it takes a lot of time on a computer. So you can try this one. It will take minutes or maybe half an hour. But what can make it faster, it can be that this large matrix, it can be written as small compound matrices, and then the multiplication between these, it will be an algebraic expression between 1/4 of these two matrices. Okay, so that's one way why this partitioning of the matrices, as it's shown here, that's where it can become useful. Okay, and these are just mathematical proofs or tricks. Regarding the matrices, we can define zero matrices. Zero matrices are entries whenever Aij is equal to 0 for all i's and for all j's. So for whatever I and j are, if they are equal to 0, we call this one. This implies that the matrix A, this is equal to a zero matrix. Okay. Then identity matrix. Identity matrices are matrices which are diagonal matrices. For example, B, let it be diagonal. Then identity matrix, it's equal to a diagonal matrix where Aii is equal to 1. Okay. For example, a diagonal matrix can be one which is 7, 0, 0, 0, 1, 0, 0, 0, minus 1. But an identity matrix, 3 by 3, is only this. And it's called identity because any matrix identity, if we multiply it with another matrix, that matrix is not going to change. Which means that if you have a matrix A times I, this will be equal to A. Okay. It's like multiplying with unity. And the identity matrices, they are square matrices. Okay, so actually, if we talk about subsets, we can state that matrix A, no, not matrix A, that's not correct. Identity matrix, it is a subset of diagonal matrices, and diagonal matrix is a subset of square matrices. Okay, so a matrix that is, for example, a matrix B, which is 4 by 3, this is never in the diagonal matrix set, okay, because it has to be diagonal to be considered. So since this is 4 by 3, it's not a square matrix, so it cannot be diagonal, okay. And at the same time, any matrix C, which is 3 by 2, it can never be an identity matrix. So it's not that. So we're assuming these will be sets. Perto în bashkësi, perto matricët e vogla janë elementet e tyre bashkësive që mund të jenë ose mos jenë. Po nuk e plotësojnë njëri kush, ngelen jashtë. So they are out of this consideration. Këtu po themi që identity matrix set është subset, është nën bashkësi e kësaj, dhe kjo është nën bashkësi e kësaj. So do thotë the square matrices set, it's here. The diagonal matrices set would be this, and the identity matrix set would be this. Okay, so they are subsets of each other. Now, I believe we talked about this one. Two matrices are equal if all the elements in these matrices are equal to each other. Then addition and subtraction of two matrices, it is defined as, for example, matrix A plus matrix B. This is equal to Aij plus Bij. So all the elements, pairwise addition, if we add these, we get a summation of two matrices. So, so this is how, maybe this definition on the board is also more generalized. So this simply states that addition or subtraction of two matrices would correspond to this operation shown in the board. We can see an example. So for example, we can have a matrix A, which is 1 minus 1, 0, 2. B can be 3, 0, 5, 1. Then A plus B, this is going to be equal to, we add up all elements with their respective coordinates. So 1 plus 3, this would be equal to 4, minus 1 plus 0, this is minus 1, 0 plus 5, this is equal to 5, 2 plus 1, this is equal to 3. This is A plus B. If we want to calculate A minus B, then A minus B would be equal to 1 minus 3 minus 2, minus 1 minus 0 is minus 1, 0 minus 5 is minus 5, 2 minus 1, this is equal to 1. Okay, so this is what is A plus B and A minus B. So if we add up this matrix here and this matrix here, so we add up like this, that makes what? This makes 4 minus 2, it's 2, minus 1 minus 1, it is minus 2, 5 minus 5, this is 0, and then we have 3 plus 1, this is equal to 4. Okay? So this is what we observe, and at the same time, we notice that this is equal to 2a, okay? Which is this matrix here. And this is equal to 2a because we have a plus b plus a minus b is equal to 2a. Okay, so it is easily observable that a plus b, which is a matrix, plus a minus b, this is equal to, so this is associated, so we can do a plus a, and b's cancel out each other, this would be equal to 2a. Now, here on the board, we have also this other matrix D. For example, here, another question is the following. What is A plus D? A, it is 2 by 2. Let's refer to A 2 by 2 to this one, because we have another A here. And if we add the matrix D, which is a diagonal matrix 3 by 3, what is this? So here, we can write this one as A is 1, minus 1, 0, 2, plus 7, 0, 0, 7, 0, 0, 0, 1, 0, 0, 0, minus 1. So what is this addition here? This addition, it is not defined. Okay, so we cannot add these two matrices. Because in order to add two matrices, they have to have the same dimension. So we can simply say, not defined. We cannot find it. It does not exist. The summation of these doesn't exist. Okay. Then, so this is just addition of them. So this is simple matrix multiplication. Then we can also define. Sorry, this is not multiplication, this is addition and subtraction. But we can define, multiplication is actually what is on the slide. We can define multiplication by a scalar. Multiplication by a scalar of a matrix, it corresponds to, so for example, the scalar, it can be lambda times A. Lambda times A, it it will be equal to lambda times aij for all i's and j's. Okay, so this is how we can define it, which means that let's keep the matrix A over there as a reference, and let's assume that we want to calculate lambda times A, which is 1 minus 1, 1 minus 1, 0, 2. And this will be equal to lambda minus lambda, 0, 2 lambda. In case lambda is equal to 3, then we can put here 2 minus 1, 0, 5, 2, 3. In this case, the multiplication by a scalar, so a scalar is just a number. This would be equal to 6 minus 3, 0, 15, 6, 9. Okay, so this is multiplication by a scalar. Then we have also the multiplication by, so these are, we can work out some examples. We can also define the multiplication of two matrices. So this is the definition, which you can read it on the slide.
No.
Yes.
Can you repeat multiplication by scalar?
Say it again.
Can you repeat it?
Of course. Yeah, sure. So the multiplication by a scalar. So far it looks like we are trying to add numbers, right? To add matrices. Is the addition always defined? No. So if you have two matrices that don't have the same dimension, it's not defined. So we have really to be careful. Okay. So sometimes if some operations are not even defined. And by the way, let's use the board this way. So the first operation that we may do, we can add two matrices, addition. Careful, not always defined, okay? As simple as it, not always defined if two matrices have not the same dimension. That's good. Similarly, the subtraction is the same. Well, similarly, of course, we can subtract two matrices, everything is good, but this is also not always defined. So if the dimension does not match. The third one, multiplication by a scalar, and of course we can repeat this, multiplication by a scalar. So multiplication by a scalar, we have a matrix construct, which in this case is, for example, this one, and we want to multiply this one by a constant number. In this case, let this general number be lambda, and if we want to multiply this 2 by 2 matrix by lambda, then we'll have here lambda times 1 is lambda, lambda times minus 1 is minus lambda, lambda times 0, 0, lambda times 2, 2 lambda. Okay, this is how this operates. Now, why could this be useful? I'm going to write it here, but I may delete this fast. Is that sometimes, and let's have some reference matrices. This is A, let's have another matrix B. Let's keep this here. B is equal to 5 minus 2, 3, 1. Okay, so this is a 2 by 2 matrix. Let's have also another matrix which is C, which is 1, 3, minus 5, minus 2, 3, 2. So this is 2 by 3. And then we can have a matrix D, which is equal to 3, 1, 2, 0, 1, 7, which is 3 by 2. Okay, so let's keep that on the board. Now we are going over the multiplication by a scalar. Let's assume for a moment that we have an expression which is equal to 3a minus 2b. Let's find what this is equal to. And if we have 3a, the a is this one here, which means that we have 3 times 1, 1 minus 1, 0, 2, 1 minus 1, 0, 2, minus 2b, minus 2, 5 minus 2, 3, 1. So then we continue. So this is again, we're just assuming that someone is constructing a polynomial where you don't have x and y, but you have matrices. Okay, so they can be sets of numbers that carry certain information. So here we get 3 times 1, this is 3, 3 times minus 1, minus 3, 3 times 0, 3 times 2, we get 6. Minus, then here we continue, 2 times 5, that's 10. 2 times minus 2, minus 4, 2 times 3, 6, and here we get a 2. So again, we are operating, we just did the multiplication by scalar. Is it clear? Okay. Then we can also finalize this, which is 3 minus 10, this would be minus 7, minus 3 minus 4, minus 7, 0, minus 6, 6 minus 2, 4. Okay, so this was multiplication, yes?
Minus 3 minus 4.
One.
Yes, it is, of course. Yes, it's 1. This is 1. Thank you for correcting this. So this was the multiplication by scalar. Now we can also say the following. What is 2a plus b minus c? So what is this? This is not defined because we can add 2a plus b because a is 2 by 2, b is 2 by 2, c, which is here on the board, is 2 by 3. So this is not defined. Okay, so we did multiplication by scalar. Then let's see what is the multiplication of two matrices. How can we operate with multiplying two matrices? Let's see the definition here on the board or on the slide, which says that if A is n by p and B is p by n, then the product is a new matrix with size n by m. Now, if you allow me, I can take this out. So the definition over there, it says that A is n by p. A. And we may need to multiply this one with b, which is p by n. So this multiplication of these matrices is defined only when these two are equal to each other, okay? Which means that the number of columns of matrix A has to be equal to the number of rows of column B, because only in this case we would have these two defined. The reason for this is that the multiplication between two matrices, it is defined like this. If the multiplication of A and B would be equal to a matrix C, the dimension of this matrix C should be equal to okay, so this is how the results has to be. And this multiplication is defined as Aij times Bjk Cik. Now, in fact, one little notation, which is very often used in several textbooks of linear algebra, what this stands for, this in fact, whenever you see one parameter repeated twice, this is a summation, okay? So if you see Aij times Bjk, instead of you are multiplying two numbers, but of course it's going to be equal to this, but at the same time, allow me to say that this will be the summation over j from 1 to whatever number it can be. Let's say j is 3. So this is A, I, J, B, J, K. This is going to be C, I, K. Okay. So in fact, this expression is equivalent to this. In this course, you might start getting used to this one. Okay. So let's think about this one in this form. For example, let's see a couple of multiplications. Now, just based on this definition, can we multiply A with B, assuming that A is this and B is this? What do you think? A is 2 by 2. We got a no here. We need to multiply this one with B, which is also 2 by 2. So, okay, so what is the constraint? What is the condition? The constraint is that these two indices should be equal. Are they equal?
Yes.
Okay, it looks like there is a probability for them to be, for this multiplication to be defined. What should be the answer? What can be the answer? A matrix C, which has dimensions of what? 2 by 2. So if this ends up into being a matrix 2 by 2, let's now try to find all the elements of this 2 by 2, which is going to be a matrix, which should have here C. What is this element? 1, 1, right? What is this other one? 1, 2. What is this element here? C2, 1. What about this? C2, 2. That's good. Then let's try to find, what is C22 first? Let's find C22. C22, that means that, let's use this expression. I is equal to 2, right? So let's not forget I is equal to 2. And what is K? 2. Okay, so let's K is equal to 2. So this is, we start with this. Then, what is this equal to? This is equal to the summation over all the possible values of j. Okay, so we have to sum over the possible values of j, but we have to write down in this expression the fixed values. Which one are the fixed values? ai. So let's write a. What is I? 2. J. Well, j is 2. Right? J is 2 because j is not fixed. J is going to be, we have to sum over the j. What is fixed is I and k alone, because we have to find C22. And let's go over here. So if this is like this, the free variable, which can change, or let's do it like this. The fixed variables, it's I is fixed and this j. Sorry, no, it's wrong. K, yes, correct. So these are fixed, because these are fixed. So these are cycling, or these are changing. Okay, so let's assume that like this. So here we have A2j times Bj what? 2, because k is 2. So we just substitute the values for I and k. Then, if this is like this, now let's notice j is what? The first index of A, matrix A, is the row. J is the column. Sakolona kaya. 2. So that means that j it can be from 1 to 2. Okay, because we have only 2 columns. That's good. So now let's continue. So this is, let's do the summation. First, let's write the term when j is 1. So this is a summation term. That means that we have to calculate first when j is 1 and then when j is 2. So all we need to do is that A21 times B12. So what was this? This was j is equal to 1. Plus A22 B22. This is the expression j is equal to 2. That is correct, right? So let's multiply these, but now, sorry, they are written somewhere in the board, but we also have a piece of paper, maybe write them more on top of each other. Teplatoria, usually idziemy polaj. So what is A21 times B12? Maybe it's better if we write it like this. One minus 1, 0, 2, times 5, 3. Okay, so A21 is where? A21 is this element multiplied by B12. First row, second column, multiply with this. Okay? And what is this? 0 times minus 2. Plus A22, which is this element, times B22, times this element. So in fact, what we are doing is that we are multiplying this row with this column. Okay? So this is what we are matching. So we are using this one multiplied by this. This is the matrix multiplication, and we find which element. What is this? This is 2 times 1. So this is 0 plus 2, 2. So it looks like this element is 2. I can write this also here, 2. Okay, then let's try to identify what is C11. And by the way, where is C11? C11 is right here. This C11, it is the intersection of the first row and the first column. So let's have a look at this and this. Okay, so what will this element be? It's going to be 1 times 5, which is 5, plus minus 1 times 3, which will make here 2. Now, if we use this formula, which we have written here, let's see for a moment, what is C11? C11, that means that I is equal to 1 and K is equal to 1, right? And this will be equal to the summation when J is equal to 1 to 2 of A. What is I?
1.
It's 1. So it's 1J and B J1, right? In fact, once we see this like this, it looks like we are going to the row of A is fixed. So we have to work with the row of A, right? But what is changing is the column, which means that we're scanning the whole row. But when it is BJ1, that means that we have fixed the column. We keep the first column, but we're changing all the rows. So we're scanning over the rows. This is what that means. Okay? So then this would be something like this: A11, B11 plus A1, B1. Sorry, B1 is here. This is 2, 2. So in principle, if you look at it like this, it's really the pairwise combination of the elements on this row with the elements in this column. So this one, it will be equal to A11, B11, 1, 5. Plus minus 1, 3. So we get 5 minus 3, we get 2. Separately, we get 2. So we can put here 2 here, 2 here. Okay. So this is how the multiplication is done. For a moment, let's try to identify what is this element here. To find this element, this is the let's say the intersection of the first row with the first column. Sorry, it's the second column. So it's this one. So then we are going to add pairwise multiplication of all the elements in this row with these elements in this column, which it will make it like this: 1 times minus 2, minus 2, minus 1, minus 3. So this is minus 3. Or, if we want to look for this number here, to return this number here, we see that this is in the second row, first column, which means that we will have to look for the second row here and the first column here, okay? So it's going to be 0, 2 times 5, 3. We have the pairwise multiplication of these elements. 0 times 5, 0, 2 plus 3, 6. Okay, so this will be the answer of this multiplication. Is it clear? So just need to check the row in the first matrix multiplied by each column in the second matrix.
Yeah, but what about the 2 that you put it on the top left?
The top left, yes. This 2 is because it is this 2. This is a combination of the first row and the first column. Okay, so it is near base plus minus near. Okay. Now we can see a couple more of examples, but since we need a space, we may delete some of this. So for example, let's try to do the multiplication of C times D. What is C times D? First of all, can we multiply C times D?
Yes.
C, it is 2 by 3. We multiply this one with D, you are correct, times 3 by 2. And these two indices are the same. So what should be the result? What is the size of the matrix that we get? 2 by 2. It's 2 by 2 because it will be these two dimensions. So the outer dimensions here, it will determine the number of possible combinations. But now let's try to see. 1, 3 minus 5. And then we have minus 2, 3, 2. Minus 2, 3, 2. And let's try D, 3, 1, 2. 0, 1, 7. 0, 1, 7. And then let's move ahead. First, we have to combine the first row with the first column, okay? Pairwise multiplication. What should we get? 1 times 3 is 3, plus 3 times 1, 3 plus 3 is 6, minus 10, minus 4. Okay, we're done with the first row and the first column. Then what is left? First row with the second column here. So let's see what the result we get from here. 1 times 0, 0, plus 3. So it's going to be 1 times 0 plus 3 times 1 plus minus 5 times 7, right? So let's see where they belong. So it's really this row, this column, 0 plus 3, 3 minus 35, minus 32, right? Minus 32. Then we are done with this possible combination. Then we have to come to combine the second row with the first column here. Okay. Then here we get minus 2 times 3 plus 3 times 1 plus 2 times 2. So here we get minus 6 plus 3 minus 3 plus 4, 1. So we got 1. We are left with one last number, and this number, it should be a combination of the second row here with the second column here. In this case, we have minus 2 times 0 plus 3 times 1 plus 2 times 7, which makes it 14, 17, 17. Okay, so this is this answer here. Similarly, now you can try and you can calculate this at home. What is D times C? What is the result of D times C? Is this defined?
Yes.
It is defined, that's true. So the answer here should be a matrix which is 3 by 3, but you can work this out on your own and try to find the answer. Okay. So this was the matrix multiplication. Out of this, okay, so here we have two examples here on the board. The question is, for example, what is the answer if we multiply A times B? What is the size of the matrix? A times B, which are shown here on the slide. A, what is the dimension of A? If we multiply this with B, what is B?
3.
4, 3. So it looks like this multiplication, it is defined. Okay, so the result, it will be a matrix, yes, it will be a matrix which is 2 by 3. So some matrix which is 2 by 3. What about B times A? What is B times A? This is not defined because B has 4 rows and 3 columns. And in this case, we cannot, this is 2 by 4, so this is not defined. And this is not defined because if we multiply the first row of B with the first column of A, we don't have enough numbers. We have 8 times 1 plus 5 times 2 plus 3 times a missing element here, so that's why we simply say that it's not defined. So it looks like this multiplication by multiplication is always defined. Always defined. Multiplication by two matrices not always defined. Okay. Because we are talking about these possible operations. Then we have also another possible operation, allegedly possible. So division, div. Now division by a matrix, this is also not defined. Okay, so never defined. So we cannot divide by matrix. A small equivalent principle or principle which we observe it here and in another aspect is the division by complex numbers. But I believe we can discuss this again later. Number complex, the square root of -1. We cannot divide by these strange numbers in the same way that we cannot divide by a matrix. But for now, let's focus on the division by matrix. Okay, so here you have another exercise. You can multiply the C times D or D times C and see what we get. Now, so these are some just some theorem or some rule that whenever we multiply matrix A times B, then the ith row of AB is given by the product of ith row of A times B. Okay, this is just something which you can observe. For example, if we are multiplying here C and D, the second row, so let's try to read this one from here. So this is the result of